Let's discuss localized versus delocalized electrons. The localized definition is pretty easy. They are not in resonance. And so here's an example of a localized lone pair. If you look at this molecule here on the left, we have a nitrogen, and from chapter 1 we would say that this nitrogen is sp3 hybridized. It has 3 CN bonds and a lone pair, 4 electron groups, sp3. Tetrahedral shape, tetrahedral electron shape, trigonal pyramidal molecular shape. And so that means that this lone pair is in an sp3 orbital. It cannot be in resonance if it's in an sp3 orbital. So delocalized must be in p orbital, must participate in resonance. So basically those are the differences we're looking for. Localized electrons are not in resonance. They're typically in an sp3 or an sp2 or an sp orbital. They are not in a unhybridized p orbital. Here's another example. This oxygen, we would say, is hybridized sp2 plus p. So at first glance you might say, oh hey, this lone pair could be in a p orbital. But if you think about it more closely, you know that the p orbital is being used with the adjacent p orbital on the carbon to make this pi bond. And therefore these lone pairs must be in one of the 3 sp2 orbitals. Therefore they are not in resonance either. So these are localized and these are localized. Both lone pairs on the oxygen are localized. They are not in resonance. Let's look at the lone pair on this nitrogen now. Is it in resonance? Well, we see one of the resonance patterns, lone pair next to pi bond, or allylic lone pair. And so let's call this allylic lone pair. And of course, if we drew a arrow pushing pattern, it would look like that. And if we drew the resulting structure, it would look something like this, which is a perfectly reasonable structure. So that gets the check mark, the seal of approval. And so this lone pair is in resonance. And so how is that, you might ask? We would originally look at this nitrogen and say it is also sp3, like the first nitrogen on the left side of this page. However, if the ability to be in resonance is there, the nitrogen will rehybridize to something that will suit resonance. In this case, it's sp2 plus p, and that allows the lone pair to exist in a p orbital. It allows the lone pair to be in resonance, in this case, the allylic lone pair pattern. And so another sort of rule is that the delocalized electrons in the p orbital must overlap with adjacent p orbitals. And now that's probably obvious. If it's in resonance, it has to overlap with adjacent p orbitals. There's a p orbital on these 2 carbons bearing the alkene, and so the p orbital on the nitrogen that has a lone pair is overlapping with these p orbitals on the alkene. And so the fact that we can draw a proper resonance pattern and a proper resonance structure means that it overlaps with adjacent p orbitals. So this is an example of where the nitrogen appears at first glance to be sp3 hybridized, but because there's the opportunity for resonance, it will rehybridize to the sp2 plus p, and thus this is a delocalized lone pair. Now let's look at the final molecule. It has 2 sets of lone pairs. Let's look at the first lone pair here, this nitrogen. We would say that this nitrogen is sp2 plus p because it has a double bond, a single bond, and a lone pair. It has 3 electron groups. That's sp2 plus p. And so we might say, oh hey, that lone pair can be in the p orbital. It can participate in resonance. Here's a resonance pattern that I observe, allylic lone pair. Let's go ahead and draw that pattern and see what we get. supposed to be a negative charge there, plus charge here. We've created some charge. That's typically not too much of a problem as long as we're following one of the resonance patterns. And we're attempting to follow that pattern here. But there's a problem with this structure. Can you see the problem with the structure that I just drew? This nitrogen now has two electron groups around it, a double bond and another double bond. Therefore, what should its molecular shape be? It should be linear. And clearly it's in a six-membered ring. It's in a circle of atoms. It cannot be linear. And so this is a poor resonance structure. Even though we followed the rule, we created a linear atom inside a ring, and that's not going to happen. And so one trick to recognizing that this lone pair is not considered the allylic lone pair resonance pattern is that the lone pair is actually on a pi bond, right? So it's part of an atom that's already part of a pi bond. And so typically lone pairs in that position do not participate in resonance. We saw an example of that over here with this ketone. We had lone pairs that are on an atom that were part of a pi bond already. They were not going to participate in resonance. They were in hybridized orbitals. They were not in a p orbital. And so this lone pair is localized. Typically when you have a nitrogen in a ring with a double bond and a single bond and a lone pair, that lone pair will be localized. So now let's look at this last lone pair on another nitrogen. Here we observe essentially a seemingly normal looking nitrogen. It has the allylic lone pair resonance pattern, which if we draw the first arrow and then we use the second arrow again that we already had, I can turn that into a resonance arrow. Let's look at the resulting resonance structure. So here is the resulting resonance structure. We've got a nitrogen with now a double bond and two H's. This should be a plus charge. And then we have our negative charge like we had before. None of that is really a problem. This nitrogen can form this trigonal planar shape. The lone pair can reside here as a negative charge. So at first glance, we might say that this is an sp3 hybridized nitrogen, just like the one over here. But the fact that this lone pair can be, if it's in a p orbital, it can be overlapping with the p orbitals that make up this CC double bond, this nitrogen will rehybridize itself into sp2 plus p. It costs a little bit of energy to do that, but it gains more energy back once it's in resonance. To be in resonance is an energy stable state. So if a molecule can participate in resonance or can do some resonance, it will, and that allows it to be a more energetically stable, a more lower energy molecule. So really our nitrogen, this one right here, has rehybridized to sp2 plus p, allowing this lone pair to be in a p orbital, which allows it to participate in the allylic lone pair resonance pattern. So this is a delocalized. So the last example here had one localized lone pair, the first one, and one delocalized lone pair, this second one on the NH2.